Hello everyone, my name is Ferit Bilgi. I am a computer science student at Bilkent University. Today I will record my Physics 101 project. My project's name is Conservation of Energy, which is about the conversion of spring potential energy into kinetic energy. My goal is to eliminate human factors while examining the law of conservation of energy using the conversion of spring potential energy into kinetic energy as a demonstration. Required equipments are air table, springs with different spring constants, precision scale, one ruler, and two wooden planks, Arduino Mega, breadboard, and the breadboard has a length of 16 centimeters, which is equal to the distance traveled by our object, jump wires, HC SR4 ultrasonic sensors. This is my experimental setup. As you can see, there are the springs. And this is the code of the sensors, as you can see there. Start mechanism. I connected a spring to there. I'm changing after every 5 experiments, and this is the Arduino Mega card. This includes our code and works with the sensors and processes the data and returns us the time, as you can see there. Here it is a sum of experiment of the sensor. This is the first ultrasonic sensor. When I do that, it says the sensor, the timer started. And after I do this to the second one, it gives the time. So my main purpose is, with the frictionless surface, I will measure the time thanks to these sensors. My main purpose is measure time thanks to these sensors on the frictionless surface, as you can see. Here it is, our new time. I attached the card to the object to provide a larger surface area because the sensors could not detect the thinness of the air table's tube. This card, which does not affect the measurement factors, provides a suitable surface area for sensors working with echo to perform measurements. While conducting measurements in the laboratory, I performed the appropriate calibration for the system after many failed attempts. Following my calibrations, the setup started working properly and I was able to achieve accurate measurements. I recorded the results of the accurate measurements immediately after completing them. I calculated the spring potential energy and the kinetic energy of an object using the spring constant, measured time, compression distance, and the distance traveled by the object. For these calculations, I used the formulas for the spring potential energy U equals 1 divided by 2 kx squared and kinetic energy K equals 1 divided by 2 m v squared. Additionally, I determined the velocity of the object using the formula v equals x divided by t. To eliminate human error, I used the Python programming language to compute these formulas in a digital environment. Since not all springs could be compressed by the same amount, the inverse relationship between compression distance and movement time was used to calculate what the potential and kinetic energies would be if all springs were compressed equally. This calculation, like the others, was also coded and executed using Python. The results were then visualized in a graph comparing potential and kinetic energies based on the spring constants. In the error analysis, different levels of errors were observed in different springs. Potential causes for these errors include air resistance, energy losses due to friction, as it is practically impossible to completely eliminate friction, and minor deformations in the shape of the springs during compression. Although there were energy losses, the relationship between the conversion of spring potential energy into kinetic energy was observed to be valid. While this relationship may not be 100% accurate in practice, the theoretical accuracy of the formula was confirmed through observations.